Hi, welcome to a video on the Dobot MG400 desktop robot arm. A local supplier, Dobot.nu, was kind enough to send me a unit to play around with. I've linked them in the description below. What I would like to do in this video is give my first impressions of the robot from the perspective of a new user. I will have a quick look at the hardware, the end effectors and the supplied software for programming. A quick disclaimer, I have no agreement with the supplier on making any type of video, no money has exchanged hands and all of the opinions expressed here are my own. I'm also sending the unit back to the supplier. Now with that out of the way, let's get started. I will not go through all of the MG400 specifications here, but just to mention a few key ones. It's a desktop robot with a small footprint while still having a significant work envelope. It weighs in at around 8 kilograms or around 18 pounds. The maximum payload is 500 grams or about 1 pound. There are 4 axes of motion. The arm can rotate around the base. It has 2 joints in the arm, and lastly the end effector can be rotated for positioning the part at the correct orientation. All of the axes are driven by proper servo motors, of course with position feedback. This enables the robot to work at high speeds, have smooth motions and be strong enough to handle the 500 gram payloads. All 3 joints in the arm and base are using a gear transmission with timing belts, which is nice and quiet. The 4th axis, to which you mount the end effector, is also driven by a servo motor. But here, no gearing and reduction is in place, so you mount the end effector directly to the motor shaft. Before starting any work, you have to enter in the weight of the end effector, so the motor drive circuit can make sure it's held steadily in position without being either too weak or too stiff. As far as I can tell, you can only enter the mass of the end effector and not the moment of inertia, which would make more sense to me. Also, as far as I know, there's no auto-tuning routine for this axis. On the back of the base, most of the connectors can be found. There are 16 inputs and 16 outputs, as well as connections for 24 volts, so you can directly power your end effector or any of your own accessories. There's also a power connector, an on-off switch, an e-stop connector, and connectivity ports like USB, a local area network, and an encoder interface for dynamic tracking of a conveyor belt. There's also an air fitting that is connected to an air line going to the front of the robot arm, so you can directly plug in a suction cup or end effector into the front of the arm, which is very nice. The arm itself seems to be made out of aluminum castings and all of the joints have roller bearings. Overall, my impression is that the build quality is very good. Having only limited experience with the unit, I cannot say anything about durability over long-term use, but from what I can see it looks like a solid mechanical platform. At the front of the arm we have the air connection, another I/O port and an unlock button that can be used to unlock the arm and manually move it around to teach it where you want it to go in your application. When doing this, the arm actively compensates for gravity, making it light to move around. This is a very nice feature, but I typically just jog the arm around to set new coordinates. That is just my way of working. The Dobot platform allows you to program it any way you like, from teaching in coordinates to scripting. You can use whatever works best for you or your application. Just for comparison, here's the new MG400 next to my own Dobot Magician robot. The Magician, as far as I know, is still being sold, but more targeted towards the educational market. Some key differences are that the Magician is smaller and the drive system is less sophisticated, as it uses stepper motors instead of servo motors. Also, you have to home the Magician after turning it on, while I have not homed the MG400 even once. It recalls its position even after being turned off. While the MG400 is part of the industrial series of robots, I see no problem using it in schools or universities for educational purposes. It all just depends on your needs and budget. The MG400 goes for a little under 3,000 euros excluding end effectors, which is more expensive than the Magician. But I think it can be justified given the larger size, more professional build quality and more advanced drive system. Okay, let's do some experimenting. In order to have any repeatability in your setup, it is highly recommended to fix the robot to a work surface. Here I'm just using some sheets of wood, but it would be better to fix it directly to a tabletop or any other sturdy work surface. The e-stop can just be plugged in and it's ready to go. Also, at a bare minimum, we have to connect the power supply and the network connection so the software can communicate with the robot. The supplied software is DobotStudio2020, which is still the latest version. The software is updated when needed, but so far they've kept the 2020 year in the name. Connecting the Dobot is very easy. When both your laptop and the MG400 are on the same local area network, the software is able to find the robot automatically. There is a catch though. The MG400 has a fixed IP address which cannot be changed. It is 192.168.1.6. For the majority of people, this works fine. My network, however, has a different number instead of the 1. Since I do not want to change this, I'm using a second cheap router set to the correct address range. This router sits in between my laptop and the robot arm. If, like most people, you are using the typical IP range, you have nothing to worry about and it will be plug and play. Here I am manually moving the robot arm. You can move all of the joints individually. As usual, the software can also use inverse kinematics. At the business end of the robot, there's a shaft where you can mount a generic end effector flange. On this flange, grippers, vacuum cups or any custom end effector can be mounted. I received the optional electromagnetic gripper and a couple of vacuum cups to play around with. The gripper is a very compact unit that allows you to pick up parts of varying sizes. The gripper size can be adjusted by screwing the supplied clamps into one of the threaded holes at the end of the gripper. This approach makes it also suitable to attach your own custom designed clamps. The gripper is then mounted onto the universal flange and secured to the 4th axis. The cable for the electrical signals has to be routed over or through the arm to the back of the robot. Since there is no cable duct available for this, I'm just using some tie wraps. If this was my own robot, I would probably replace some of the existing cable clamps under the arm with a design that has a clip of some sort to hold the additional cables. It is important to leave enough length of the cable at the joint to make sure that the arm can still move freely. By the way, the 4th axis to which the gripper is mounted can make up to 2 full revolutions, which should be plenty for most applications. All that remains now is to connect the cables for power and closing the gripper to the I/O port on the back of the robot. Any output port can be used. Since I do not have any industrial looking parts at home, I will do a demonstration with simple wood planks. You might recognize these as parts of a construction kit that is sold under the Kepler brand name. They're quite consistent in size, so a good candidate for some pick and place testing. I'll give them back to the kids when I'm done. In order to make an array of parts that the robot can pick from, I printed the template with rectangles to match the parts. Something like this only works when you align the template perfectly to the coordinate system that you're using. Also, aligning the gripper to the center of the part and having the 4th axis at the correct angle all add to the accuracy and the end result. The end effector slightly tilts apart when opening, but this could be fixed with some wider grippers, but for this demo I will leave it as is. Here is another example that is based on a simple program where each part is rotated slightly compared to the part below. Now let's check out another type of end effector, the vacuum cup. This type of end effector is quite versatile. It can be used to pick up parts of all kinds of different sizes as long as they have a somewhat smooth top surface. It is necessary to adapt the program to this type of end effector, especially with light parts. Even after the vacuum is turned off, it might take a while for the part to release due to residual vacuum in the lines. One of the possible solutions is to apply a short burst of compressed air when the part has to be released. This actually works very nicely. The MG400 offers the ability to use an end effector that is off-centered compared to the fourth axis and to compensate for the offset with inverse kinematics, so you don't have to do any math to keep the end effector in a fixed position when it's rotating. This does require an initial calibration of your specific end effector. In this procedure, you will align the tip of the end effector with an arbitrary reference point. Then rotate the end effector and position it back over the reference point. Using this calibration, the software can compensate for the offset. This can be demonstrated by just rotating the fourth axis manually, while the tool coordinate system for this end effector is selected. To do a functional test with an off-center end effector, I printed a bracket to hold a pen that was borrowed from my Dobot Magician. Although this did not turn out the way I expected, it did teach me a bit about how the fourth axis works. The fourth axis is directly driven by a servo motor. In fact, the end effector is mounted directly onto the motor shaft. This enables a very compact setup, but it does mean that it's more sensitive to an external force applied to the end effector, such as the dragging forces of a pen on paper. Now, there's nothing inherently wrong about this setup, you just need to be aware of the limitations. I would not consider this suitable for an end effector that is expected to apply any significant amount of torque on the fourth axis. Having said this, it can be used for lighter applications, like glue dispensing for example. If you need more rigidity when using the fourth axis, make sure to place your end effector in line with the motor shaft, instead of being off-center. Also, a heavier end effector might help, as this will enable the fourth axis to have a more rigid positioning control loop. Anytime you place a new end effector on the fourth axis, you have to indicate the weight. This will have an effect on the control settings for the servo motor. Entering a number that is too high might lead to oscillations, so make sure to put in a number corresponding to the weight of your end effector. To see how you can integrate the inputs on the back of the Dobot into your project, I made a simple test program that will move the robot to a different position when a button is pressed. The input ports respond to a 24 volts DC input signal. I'm placing a button between the integrated 24 volts connector at the back and the randomly selected input ports, number 16 in this case. Make sure to double check your connections and power on the robot. We can test if the input signal works by opening the I/O sidebar. When the button is pressed, a green indicator in the software comes on. This is the simple program that I made. It loops continuously and checks for the status of the button. The robot then moves to either one of two positions, depending on whether or not you're pushing the button. So this seems to work fine. The MG400 has 5 different levels of safety to protect the user while being in the working area of the robot. I'm using level 5, which is the safest setting. If the arm detects that there is a collision, it will stop and it will give an alarm. Only limited force is required to stop the robot arm at level 5. I also tested the level 3 setting, but there's quite a bit more force needed to trigger the alarm, so I'm sticking to level 5. It's good to see that there's a possibility to set the safety level based on your own preferences and use case. Now for some static tests of position repeatability. I place a dial test indicator at several positions to measure the repeatability from different directions. I was pleasantly surprised as it kept returning to the same position to within a couple of microns. This is far better than I expected. I do not have any means to test the repeatability in a dynamic situation when following a specified path, but measuring the position repeatability in a fixed position does help to estimate how it will perform in situations where the robot needs to stop at a specific coordinate. Finally, I will have a look at the provided software program. There are 3 ways you can use for programming, ranging from basic to advanced. The teach and playback as well as the Blockly options are easy to use and intuitive, while still offering most of the functionality. The script option allows more flexibility for people that like coding in a more traditional way. If we first have a look at the teach and playback option, you can see all of the commonly used commands on the left side of the screen. These are things like selecting a specific move command, speed, or the activation of an output port that is used for an end effector. Variable names can be declared here to reference in your program, and also the use of typical things like if statements and loops are supported. When you select a command, it's placed into the screen on the right side where you will build your program. The steps in your program can be moved around, edited or deleted as you see fit. The Dobot Blockly interface is even more visually oriented. On the left sidebar, the commands are grouped into logical sections and color-coded. The control section contains all of the common types of if statements and loops. Anything that you want to use in your program can simply be dragged into the working area. The operator section allows you to add some logic or math to your program. Also with Blockly, you can create your own variables for using your program. After making a new variable, it can be set to a specific value or used in any equation. From the move section, you can add motion commands, varying from linear moves to jump moves to arcs. For what I'm showing here, don't try to find any logic to this program. I'm just dragging some random commands to show the functionality of the software. I will share some examples on my website, linked in the description below. In the I/O section, commands can be found for setting outputs to high or low, as well as reading the status of the inputs. There are several more sections that I did not use in my testing, like Modbus, Vision, Palette and others. Feel free to look at the online manuals for all of the features. The Vision commands should work with the Dobot Vision module I tested earlier. I will leave a link to that video in the description below. A vision system enables an automated system that is far more flexible compared to programming alone, so I would highly recommend to look into that as well if you're thinking about automating your process. There's also a script environment. All of the available commands are again listed on the left side of the screen. Clicking them adds it to your program, and if you double click on the icon next to the command, it includes the full syntax. There's also a help button for each command that provides you with a short explanation. I've not used this environment myself, so I cannot really give my opinion on it, but at least you know it's available if this is your preferred method of programming. My overall impressions of the software is that it's a cohesive experience and very intuitive, making it easy to use and most importantly fun to work with. And to wrap up this video, I would like to discuss some pros and cons. Starting with the cons, I would say that the fourth axis has limited capability in terms of dealing with high torque applications. Besides that, it can start to oscillate if you enter the wrong mass for the end effector. Also, it emits a high-pitched sound that you may have heard throughout the video. The noise level is very low, but the high-pitched nature of it makes it a bit annoying if you're sensitive to this. Having said this, I did get used to it, and you can always disable the robot when programming it, making it completely quiet. The overall noise level of the robot is very low, even when taking the fourth axis into consideration. The other things that I would like to see improved are some minor bugs in the software. When you give a name to an I/O port, for example, it's not consistently updated in all of the menus. Also, the 3D display is a bit glitchy, sometimes showing the arm in impossible positions. I was rarely looking at this 3D view, so it's not a big deal, but still something that should be fixed in my opinion. The last thing I want to mention is the fixed IP address. As mentioned before, there's a workaround if you can't use this IP address, but it would be nice if you would be able to set it yourself. Now on to the pros. The arm has a professional build quality with an all-metal frame. For all of the connectors, wiring and injection molded covers, it looks like they've used quality parts. This is good to see considering the relatively low price, which is another pro by the way. There is a large number of I/O ports that can be used freely within your projects. Several different end effectors are available and the robot can work together with a vision system, and it has a conveyor belt synchronization option. Furthermore, there are several ways to program the robot, so there should be an option to match your preferences and skill level. From what I can tell, the motion system on the robot is very accurate, and for the small form factor it has a relatively large work area and high payload of 500 grams. So I hope you've enjoyed this quick overview of the MG400.